As mentioned, I will talk to you about the road towards fully cellulosic barrier materials and possible alternatives to plastics. And of course, welcome questions at the end of the presentation. You should see my presentation now. So just to mention that two of the projects that I will mention during the presentation have received funding from the Bio-Based Industry Joint Undertaking under different grant agreements. Before going into the, let's say, subject itself, I wanted to say a few words in one slide about CTP. We are an industrial and technical center serving its industry, which is the pulp and paper industry, with the goal of creating value to strengthen the positioning of the pulp and paper industry all over the world. And to do that, we try to contribute to the development of the product mix by working in new market, developing new paper functionality and new process technologies, and working as well with the downstream sector, for example, the food packaging sector. And we do that through advanced industrial research, which is exploratory, some innovation, technology transfer through consultancy and expertise services, and analytical services as well. So as mentioned today, I will try to give you a bit of context about the search for alternatives to plastic materials, why we are looking for that now, and present to you two processes that we hope could lead to materials of the future and to hopefully fully cellulosic barrier materials. Those two processes are the wet lamination of microfibrillated cellulose and chromatogeny, before concluding on this presentation. So, but first, a bit of context. You are probably all aware of current regulatory context that is shifting more and more. And for example, the single-use plastic directive is part of this context, in which producer responsibility is extended. Reusable solution to single-use plastics are supported. Reduction targets are very ambitious, and some bans on some materials are also implemented through this directive. This is one example. Another one is specifically in France, the law that's called the Egalim law, which targets a balance of commercial relations in the agricultural sector. It also targets to promote healthy and sustainable food. And specifically in relation to plastics, it targets the decrease of plastic uses in the food sector. For example, through forbidding trays to cook, reheat, and serve food in collective catering, through forbidding plastic straws, through forbidding plastic bottles in school cafeterias. So those are strong actions from Europe, from different members of the Union that target plastic packaging. But that's not only coming through regulatory context. Pressure is also applied from consumers, for example, because more and more consumers' awareness is rising, in part due to a strong media coverage of littering, plastics in the ocean, and so on. And NGOs and foundations have more and more strong action to accelerate the transition to a circular economy. So the trend that we see is really trying to shift away, or at least partly shift away from plastic materials. One possibility to do that, and I'm not saying it's the only one, of course, but it's one of the possibilities to go towards cellulosic materials, because cellulose is a bio-based polymer, renewable, biodegradable, recyclable, so a really strong contender to shift towards packaging that are part of the circular economy. Unfortunately, if it were that easy, we would have done it long ago to switch, for example, from plastic bottles to paper bottles. This is just here one example among many others. And there's been a lot of communication recently in the media about the possibility to shift to paper bottle. But it's not just about producing, for example, the bottle that is made from paper. There is a lot of requirements to take into account to produce a packaging material. We won't describe them all here that are listed on this slide. This is not the goal, of course, but it is just to tell you that it is very, very complex to create a packaging material that answers requirements both for protecting the food, managing converting, sealing and recyclability, biodegradability, visual aspect, mechanical resistance, and so on. There are many, many factors to take into account. If we go into more details in the barrier requirements, which is one of the requirements that packaging has to answer, then we can see that there are many requirements in terms of barrier depending on the food that is packaged into the packaging material. Some food need barrier to be protected against water vapor, against oxygen, light, aromas, contaminants, and so on. So the combination of the product that is packaged and their shelf life and needs to be taken into account in order to define the barrier specification that's needed for a packaging material. All of this to say that even if paper and board are very good in terms of an environmental ranking, because as I said, it's a renewable, biodegradable, recyclable material. On its own, before converting, barrier performances that are required for most food products, most foodstuff, are not achieved, and substrates need to be transformed, converted with a barrier solution in order to achieve the requirements needed to be able to package foodstuff, for example. And here you can see on this graph that the vast majority of barriers that are used today on paper and board are extruded polymers, mainly fossil-based, petrol-based, sorry, aluminium, wax, silicone, fluorinated products. So materials that are not sustainable or not integrated in a circular economy. And the trend that we see more and more is how to try to phase out aluminium and polyethylene and to replace those barrier coatings, those barrier layers with bio-based materials in order to have paper and board packaging that are bio-based, composed as much as possible of fibers that could be recyclable in a paper stream, paper recycling stream. How to remove fluorinated compounds from paper and board, and really the question that we, I think, are asked really often now is it possible to produce a 100% cellulose packaging with the technologies today? And this is what I'm going to try to answer, or at least give you hints about today. At CTP in the recent years, we have worked on two specific barrier technologies that we hope are barrier technologies of the future, and that bring good barrier performances to papers and board substrate without adding plastic materials on top of it. The first one is called microfibrillated cellulose wet lamination. And this technology, is a process that deposits and dry a layer of MFC at the surface of paper and board. I will go a bit in more detail on the technologies right after. And the second technology is called chromatogeny. And this one is a process that chemically modifies the cellulosic compound, so the cellulose substrate, in order to turn it hydrophobic. But let's go into a bit more detail on MFC wet lamination first. MFC, or microfibrillated cellulose, is a product that is produced from cellulosic fibers. But these microfibrils have a small diameter and small length. They are fibrils, really, and they can be used as a coating layer on top of paper and board in order to obtain an excellent barrier to grease, to oxygen, to contaminants, and to aromas. As you can see here on this picture on the right, you have an uncoated board which has been put into contact with oil for 30 minutes. So of course there is a big oil stain on the board after contact, and on the right picture, the exact same board coated with a layer of microfibrillated cellulose. And on this material, after 30 minutes of contact with oil, as you can see, the barrier is perfect and there is no staining of the oil on the material. So the barrier is really excellent. And the advantage of microfibrillated cellulose is that it is, of course, cellulose, so a bio-based material, biodegradable, recyclable in a conventional paper recycling stream, like paper and board, but with the additional advantage of bringing barrier. The drawback, however, of this MFC material is that it's manufactured as a gel, so it has a very low solid content, of about 2 to 4%. So the rest is water. But it's highly viscous. So traditional coating processes that are used in the paper making industry are not adapted to apply it on papers and boards, and it was therefore necessary to find a new process, a new concept to be able to deposit this microfibrillated cellulose layer on the paper or board substrate in order to obtain this barrier. And this is where the MFC wet lamination process came to life. So the idea is that the wet MFC film is formed by filtration of the MFC through a wire, and only once this MFC film is formed, then it is reported on a paper or board substrate, and since it is still wet, it then naturally adheres to the paper substrate. So there is no glue that is used to join the MFC layer to the paper or board layer. It's all natural adhesion, and the paper on which the MFC film has been applied is then simply dried before being rewinded, and you then have an MFC stratified paper at the end of the machine. This technology, so as I said, is targeted to bring excellent grease, oxygen, and contaminant barrier to paper and board. MFC are cellulose, a very hydrophilic material, so it does not bring either water barrier or water vapor barrier. This is not the target of this kind of layer. And up to now, the technology has been developed at lab scale to begin with, so at technology readiness level 3, and is currently being pilot scale, sorry, on a small pilot machine that's been installed at CTP at the end of 2019, so a bit more than a year ago. And it requires, therefore, dedicated equipment to develop the process and produce samples for testing and proof of concept. And this MFC laminated material is afterwards fully compatible with further surface treatment to bring other barrier performances to it, such as coating, laminating, and so on. To give you a bit more detail on how the material is produced at laboratory scale, here you have the equipment that is used, and the idea is simply to filter an MFC suspension on a wire using some vacuum. Then to replicate this MFC film on a paper substrate. And then using a plating press that you see here in the middle to press the MFC film and paper together between blotting papers in order to join the two layers, and then to finish drying the material using conductive drying under stress, for example, in a flat dryer or in a half moon dryer. And then when you peel the blotting paper, you have the remaining MFC wet laminated paper. To go into a bit more detail about the performances of the paper, because I mentioned we can reach excellent oxygen, grease, and contaminant barrier. I've shown you the grease performance, but here you have on the right the oxygen transmission rate that we can reach with an MFC covered paper. And as you can see, with MFC laminated paper using about 16 to 18 grams per square meter of MFC, then we reach barrier performance and OTR at 23 degrees and 50% relative humidity, which is in the range of 2 to 5, so quite a good performance, bearing in mind that the initial substrate showed absolutely no barrier performance to oxygen at all. And the addition of the MFC film is possible both on mineral-coated paper or on directly paper itself or board itself. It really depends on the surface chemistry of the material, but most paper and board show good addition to with this MFC film. I also mentioned that the barrier to contaminants is excellent. And here we have done some evaluation of the transfer of contaminants through the barrier by using a donor sample that was spiked with selected substances. And here the selected substances were MOSH and MOA surrogates, so mineral oil surrogates. And as you can see, the migration of these contaminants was reduced through the barrier by more than 90%. On the red, on the graph, you see the migration without barrier, and in green, you see the migration through the MFC layer, which was significantly reduced. So that was MFC wet lamination. And as you can see here on this picture on the right, this is an MFC film that is being peeled from paper or board substrate. So this is what an MFC wet laminated material looks like. Then the second process I would like to talk about today is chromatogeny. Chromatogeny is a green chemistry process that brings hydrophobicity to hydrophilic reactive substrate. This can be papers and boards, this can be lignocellulosic fibers, polyvinyl alcohol, starch, some minerals, for example. And it's a solvent-free technology that is suitable for ready-to-read processes. The first developments in the paper industry have been applied to papers and boards, and the idea there is to bring water resistance to the material while keeping converting ability, recyclability, and biodegradability of the material. It doesn't change those properties. And it can also be applied to coated papers, for example, polyvinyl alcohol coated paper, in order to protect the sensitive, water-sensitive barrier. As you may know, polyvinyl alcohol is also a hydrophilic material, very soluble in water. So to protect this barrier from moisture, still keeping the recyclability and biodegradability performance of the material. So the basic principle of chromatogeny is to use the reaction of fatty acid chlorides with hydroxyl group in order to obtain fatty esters that are grafted on the paper. So the idea is there to protect water-sensitive material by grafting a fatty alkyl chain, so starting from a fatty acid chloride on the surface of a layer that contains an hydroxyl group. Here you can see that the fatty acid chloride reacts with the hydroxyl group, and that an ester bond is formed with the material. And in order to do that, the fatty acid chloride is deposited as a liquid on the material in the range of 0.2 to 0.5 gram per square meter, so a really very, very low amount of fatty acid chloride, which is enough to get this ultra-fast solvent-free reaction and hydrophobize the paper. So as you can see here on these two examples, this is a paper that's been treated using chromatogeny. That's been first coated with polyvinyl alcohol and then grafted using chromatogeny. And we see that it is perfectly hydrophobic. So the water rolls on the surface of the material without wetting it, and that the oil here, it keeps the barrier to grease, and the oil does not penetrate into the substrate. Chromatogeny has been developed now up to industrial scale, specifically in South Korea, where there are 2 industrial machines. The first one was started in 2015, and the second one started in 2018. And before that, it was invented in 1997, so it took quite a few years to bring it first to lab scale and then to pilot scale in 2010, sorry, before moving on for different projects to bring it towards industrial scale. The main target and market of these technologies are uncoated papers and boards. So the idea there is to really improve the water resistance of cellulosic-based material. For example, to manufacture waterproof paper. Here you have some example of markets that can be imagined for such material, such as simply corrugated board that would be resistant to rain, some health and medical paper, filters, paper that can be used for agriculture, so for working outside but don't get wet, paper that selectively absorb oil but not water. Those are all applications that can be imagined. As for polyvinyl alcohol coated papers and board that can be grafted with chromatogeny, then the idea is to develop medium and high barrier performances for this material. And here we can imagine applications such as release paper. This is actually the target of the industrial machines in Korea. Baking paper, sacks and bags, cups, for example, can also be an applications. So there are plenty of ideas and markets for such material with those performances. And speaking of performances here of grafted papers and boards, here are some numbers of the barrier performances and other performances that can be reached. As you can see on uncoated papers, then the idea is really to improve the hydrophobicity of the material, so to really lower the water absorption capacity and to bring a high water contact angle of the material. And on coated PVOH coated paper and board, then the water absorption capacity is even more significantly reduced. So we have an excellent barrier to water, excellent water repellency. We keep the excellent grease barrier of the polyvinyl alcohol. And we get actually at 23 degrees and 50% relative humidity, quite good water vapor barrier, which unfortunately is not that good in tropical conditions. So these are things that should still be improved. And this material, thanks to the polyvinyl alcohol layer, is also an excellent barrier to oxygen and mineral oil. And as I mentioned earlier, this does not change the recyclability, biodegradability, sealability, printability of the paper substrate. Food contact compliance is ongoing. So we are investigating this. So to conclude on these two processes, I would like to mention two European projects in which we have worked on these different processes. The first one is SharePack. It's finished last year, so it ran from 2017 to 2020. And in that project, the idea was to develop a renewable, biodegradable, and recyclable flexible paper-based packaging material. And in that project, wet lamination of microfibrillated cellulose was used in combination with coating of biopolymer in order to reach both oxygen contaminants and water vapor barrier performances needed for such packaging. And the second project is called Cellulosic and is ongoing. And there the idea is to target a high barrier all cellulose packaging materials, so using both MFC wet lamination and chromatogeny grafting to produce 3 different proof of concept that you can see here that are clamshells, cups, and trays. You can find more information on these 2 projects on their websites. So as you saw, we have different technologies, processes that could bring interesting barrier performances to paper and board substrates without requiring the use of plastic materials. These are chromatogeny and MFC wet lamination, which target different barrier performances, water for chromatogeny, grease, oxygen, and contaminants for wet lamination. That can be used in combination with different barrier coatings to bring additional barrier performances, for example, to water vapor, because this is not really targeted by those 2 technologies. And that in the future, and this is really the objective, could really be combined together in order to bring all the necessary barrier performances to paper and board substrate in order to really produce fully cellulosic barrier material that don't require the use of polymers, and to possibly replace some of the polymers that are currently in use on the market. So to conclude, I would like to say that we really hope that paper and board are one of the packaging material of the future due to its strong appeal for circular economy, for answering environmental concern, being bio-based, biodegradable, recyclable, being safe to put in contact with food, and being easy to transform and convert in order to form packaging. So thank you very much for your attention during this presentation, and I'll be happy to take a few questions.